Now we come to ring exercises. Exercise 46. We have to show that this set is not a subring of the ring of integers. You know that this set 2z denotes the set of all multiples of 2, all integer multiples of 2, or in other words, this is the set of all even integers. Like that, this is the set of all multiples of 3, and this is their union. Note that two and 3 both belong to this union. Because 2 is an even integer and 3 is a multiple of 3. But their sum does not belong to the union. The sum 5 is neither even nor a multiple of 3. Hence, this is not a subring of the ring of integers. It is not even closed under addition, so how can it be a subring? It is not even a subgroup under addition. Next exercise 47. Determine the smallest subring. Of the ring of rational numbers Q that contains this rational number 1 over 2. That is, find the subring S with the property that S contains 1 over 2. With the property that S contains 1 over 2 and if T is any subring containing 1 over 2. Then T contains S. Contains S as a subset. That's what we mean by the smallest subring of Q that contains 1 over 2. So we are going to guess the subring, and then we will prove that it has the desired properties. Let S be the set of all rational numbers which look like this. m divided by 2 to the power n, where m is any integer and n is a positive integer. Clearly, S is a non-empty subset of the set of rational numbers. Naturally, in fact, S will be an infinite subset. Let m1, n1, m2 and n2 be integers where n1 and n2 are positive. Then this is one element of S, this is another element of S, m2 divided by 2 to the power n2. We are taking their sum, and that sum, you of course know, will look like this: m1 times 2 to the power n2 plus m2 times 2 to the power n1 divided by 2 to the power n1 plus n2. Now n1 and n2 are positive integers, so their sum is also a positive integer, and this numerator of course is some integer. So this has the form to be in S. This belongs to S. The additive inverse of this element, the negative of this number, is equal to minus m1 divided by 2 to the power n1. Again, because m1 is an integer, minus m1 is also an integer, we haven't done anything to the denominator, so which is a positive integral power of 2. So this again belongs to S. These two things together say that S is a subgroup of the ring of rational numbers under addition. But now we are also going to see that the product of these two things again belongs to S, and m1 m2 divided by this, so this belongs to S. Thus S is a subring of the ring of rational numbers. If you want, you can make the intermediate conclusion that because of these two things being in S, that S is a subgroup of Q under addition. And then you can write this and then finally conclude that yes, because of all these things, S is a subring of Q. But I have chosen not to write that subgroup part because it's understood. It is a part of that and it's contained within it. So we have just shown that S is a subgroup of Q and is a subring of Q. Also, clearly that rational number belongs to S. For that you just choose both M and N to be 1. Now let T be any subring of Q containing this 1/2. We will now prove that T contains S. That means every element of S is also in T. We first show that fine. We first show. We can show this, the fact that every element in S is in T. This can be proved by, of course, showing that all these elements are in T, but in showing that we are going to apply induction on N. N is a positive integer. So let us instead write like this. We now show by induction on N that M divided by 2 to the power N belongs to T for all integers M and for all positive integers N. And in this process of induction, we are going to keep M arbitrary. You will see the induction that it will be clear how we are going to proceed. Since so I want to prove this thing at once, but the question is, can I do that without doing anything to M, taking M arbitrary? The problem that I immediately face now is, how shall I get the basis for the induction? In that basis, small n will be 1. So I will be dealing with numbers of the form M divided by 2. Now that itself will need an induction. Okay, so we cannot immediately get the basis at once. Since T is a subring zero divided by 2 belongs to T. Okay, suppose m divided by 2 belongs to t for some integer m greater than or equal to 0, for some non-negative integer m. So now, because we are in the case where small n is 1, we are now here itself we are applying induction on m. This however will not give us all the values of m, because m unlike n can be negative also. So we are going to handle the negative m's afterwards, after we settle the cases for non-negative m. And for non-negative m we are applying induction on m. Then m plus 1 divided by 2, which can be written as m divided by 2 plus 1 divided by 2, this belongs to t. This belongs to t, that is our induction hypothesis, our supposition. And this belongs to t, that comes from the assumption that t is a subring containing 1 over 2. So by induction, m divided by 2 belongs to t for all integers m greater than or equal to 0. But because t is a subring and t contains all these elements, so t will also contain their negatives, their additive inverses. Since t, let us just write explicitly, since t contains the additive inverse of any of its elements, we have, so if you take a specific value of small n, which is a positive integer say, then its additive inverse equals minus m divided by 2. So that corresponding number also belongs to t. We can write directly that this belongs to t for all integers n. So this belongs to t for all integers m and n equal to 1. This is the basis for our original induction. Now we make the induction hypothesis for the original induction. Suppose m divided by 2 to the power n belongs to t for all m belonging to the set of integers and some positive integer t, n. We have seen the case n equal to 1. Now we are taking a general positive integer n, but in all these things, for all m that is included. Okay, so that is a part of the induction hypothesis as well. Then okay, now our induction is not on m but on n. So we keep that in mind. M is arbitrary. So now we are going to look at the case where we have n plus 1 in place of n. And this is equal to this first number belongs to T, that is our induction hypothesis, irrespective of the value of m, the numerator. And this of course is in T, so their product, because T is a subring, so their product belongs to T. Hence, by induction, for all integers m and all positive integers n, we thus have S as a subset of T. So in that sense, S is the smallest subring of Q containing 1 over 2. And there is a similar one. The next exercise is similar. Here in place of 1 over 2 we have 2 over 3. Determine the smallest subring of same thing. That contains 2 over 3. I won't write anything much. I'll just simply write the candidate for the subring. You have to show the rest of the things. That the set that I am going to write here is actually a subring of Q containing 2 over 3, and it's the smallest such. That you can prove similarly. Okay, you show that this is a subring of Q which contains 2 over 3. Containing 2 over 3 is almost obvious, and it is the smallest subring of Q that contains 2 over 3. Okay, so this is left to you. Let's move on. (49) let R be a ring prove that a square minus b square equals a plus b times a minus b, our familiar high school formula from calculus. From calculus I'm saying, from algebra. That thing is true in a general ring if and only if the ring is commutative. Is a plus b times a minus b if and for all a and b, of course, in R if and only if R is commutative. Solution: assume that R is commutative. Then for any elements a and b in R, a plus b times a minus b is equal to, let us go step by step, okay. A times a minus b plus b times a minus b. In this step we have used the right distributive law in the ring. Now we are going to use the left distributive law in each of these terms, and additionally one ring. Let me just break it down even further. And oh, the rain is heavy, quite heavy. A minus b really means this, plus and now we use the left distributive law two times, once here and once here. So this we get AA plus A times minus B plus BA plus B times minus B. AA is of course A square. Now in place of A times minus B, we write minus AB, minus of AB, that means the additive inverse of AB, which ideally we should have written plus of minus of AB, but let's not be that rigorous, and in fact we don't use bracket. Okay, so we get this, and this is one of the elementary properties that is true in any ring. And here we have BA, and just like that here this one will be minus B square. So A square minus AB. Now because R has been assumed to be commutative, so BA is AB. So these two things cancel out and we are left with A square minus B square. Okay. Conversely, assume that a square minus b square equals a plus b times a minus b for all elements a and b in the ring. Then a square minus b square is equal to, we have already seen this calculation, I mean the how we multiply these things, these two things, how we multiply the terms out, and we can use that here directly. This we can write. Changing BA to AB, that of course we cannot do. We can write before that a square minus AB plus BA minus B square, which implies 0 equal to minus AB plus BA or AB equal to BA. We have cancelled a square and minus b square from both sides. What is the justification? The justification is the cancellation loss that we have in this group. The ring is a group under its own addition, right? So in that group, this is an equation, and you can cancel same terms from both sides of the equation. So doing that, finally we have got this, and this just tells us that R is commutative. So the familiar elementary algebra formula, this one, is true for numbers, because the kind of numbers we usually work with, they come from systems which are all commutative. Real numbers, complex numbers, rational numbers, integers, etc. Hence, R is commutative. So that's just the solution. 50. Suppose that R is a ring and that A square is equal to A for all elements A in R. Show that R is commutative. This type of rings, where the square of any element is the element itself, are called Boolean rings. It's named after the English mathematician and logician George Boole. and they are always commutative. So now we are going to show that. Let A and B belonging to R be any elements, then we perform two computations. We concentrate on this element ABA minus AB. Let us see what we can do with this. Because every element in the ring is its own square, so this also would be equal to its own square. We are going to use that fact. ABA minus AB whole square, which is just this ABA minus AB times ABA minus AB. Now we carefully multiply the terms out. We won't show that much detail now, we will do it somewhat directly. For example, ABA times ABA is ABA square. Then ABA times minus AB is minus ABA times AB. Let us first write show the multiplication, and then we will further do what we can do with these products. Then by this one minus AB times ABA, and then finally minus you will get plus, and all these things are true in a general ring, like as if we are working with numbers, ordinary numbers. Okay, now ABA whole square is ABA because every square equals the element itself, minus. You can see that these two things will give you A square, and let me show the thing here, AB. This becomes AB A square B. A square becomes A, so we have got AB whole square, which then again becomes AB. So this second element, second term is AB, minus, in the third one you can see that you have AB, so AB whole square, that will become AB, and along with that there is this extra A, and finally plus AB whole square will be AB. So what are you getting? ABA minus ABA, they vanish, minus AB plus AB, they also vanish, so you get 0, which implies so that means this thing has become 0. So ABA is equal to AB. Also, let us now calculate ABA minus BA in this manner. This will be ABA minus BA whole square like before, but we have to be careful. So the first one of course is ABA square, then this times this minus ABA times BA, then this times this minus BA times ABA, and finally plus BA whole square. So we get ABA for this one. What happens here? Minus BA give us BA, because BA whole square, along with this first A, that is just ABA. And here what happens? AA, they give us A square, which becomes A. So BA, that means BA whole square. So minus BA, and this of course is plus BA. This let me just show this or see this calculation myself below. BA square BA, okay, so this becomes BA, which is BA whole square, that is BA. Yes, again we are getting 0, which implies ABA is equal to BA. So ABA is AB as well as BA, so AB and BA are the same thing, and that proves commutativity. So AB is equal to BA, hence R is commutative. That is 50. Next 51. Give an example of a Boolean ring with 4 elements. With 4 elements, and another one, give an example of a Boolean ring with infinitely many elements. And these examples are there in the text itself. This is a Boolean ring with 4 elements. And this infinite direct sum of z to these rings infinitely many copies of z2 or z2 are involved here is a Boolean ring with infinitely many elements. It's obvious that this is a finite set, whereas this is an infinite set, but you please verify that these are actually Boolean rings. In them you take any element, in each one of them you take an element, take its square and make sure that you get the element back. Okay, so I am leaving that to you. And finally there is one this last exercise of this set of exercises. Okay, I need a little bit of ink. If A, B and C are elements of a ring, does the equation always have a solution x? A linear equation involving A, B and C. The type of equation which we encounter first in our high school algebra when we are introduced to equation solving. Linear equations are the first type of equations we encounter. A linear equation, a single linear equation in a single variable. So that can also be considered in a general ring. So A, B and C are ring elements coming from some ring. Does the equation Ax plus B equal to C always have a solution? That is, one always have a solution x. That is one part of the exercise. If it does, must the solution be unique? That is another part. And finally, answer the same question given that A is a unit. A is a unit. So we have to first say what happens to this equation in a general ring. Does it always have a solution? And the answer, of course, is no. The equation does not always have a solution. In particular, not like this. For example, ax plus b equal to c does not have a solution if a is equal to 0 and b is not equal to c. You may object, you may say that this is cheating. If a is equal to 0, then there is no equation, but nothing has been said about a, b and c. No, they can be any ring elements. So I can conveniently give a very easy situation where there is no solution. I take a to be 0, so that whatever x you take here, you are going to get 0. So x does not have, x loses the power to influence this equation. And by choosing, so this left hand side is going to be equal to b and the right hand side is c. So if I choose b to not be equal to c, then the equation cannot be satisfied. So there will be no solution. And then even when there is a solution, will that be unique? That is also not the case. Uniqueness is not guaranteed. If ax plus b equal to c does have a solution, it is not necessarily unique. And regarding this taking a equal to 0, let me just tell you that even if a is 0, that is an equation technically. It won't be a linear equation, but it's an equation after all. It is not necessarily unique. Consider the elements a equal to, now we are going to consider matrix ring. So as A, I will take 0 1 0 0 0 0 0 0 0 this matrix, and B equal to C equal to, say, the 3 by 3 identity matrix. In the ring of all 2 by 2 matrices over the field of real numbers, that is 2 by 2 matrices where the entries are 3, I am saying 2, 3 by 3 matrices where the entries are all real numbers. Note that x1 equal to 0 0 1 0 0 0 0 0 0 and x2 equal to 0 0 0 0 0 0 1 are two distinct solutions to the equation ax plus b equal to c. Let us just see, let's calculate with x1, that let us see, verify that x1 is actually a solution. You can see that because we have chosen b to be equal to c, we are expecting ax1 to be the 0 matrix, and that is the case, which we can quickly verify here. So I have taken as many zeros as I can in just now I have noticed one more thing. Anyway, let's just see this. There is in fact no need to consider a non-zero A. You can take A to be the 0 matrix. If you do that, then, and with B equal to C, you can take any x as the solution. However, let's just go with what we have taken. So what is ax1? And x1 is this one, 0 0 1 0. Now this will be what? First row, first column. First column is 0, so you get 0. First row, second column is also entirely 0, so you get 0. First row, third column is the only combination where we have non-zero entries in both of them. 0 times 1 is 0, plus 1 times 0 is 0, plus 0 times 0 is 0. And the other rows are of course 0, so they will give us only 0. So we are getting what we want. So uniqueness is not guaranteed. This, however, is not a part of the solution. You can make it a part if you want to supply those details. I choose not to. Okay, now this entire thing under the condition that A is actually a unit. A is an element in the ring which has a multiplicative inverse. Note that A equal to 0 and A equal to this, these are not units in this matrix ring. Now assume that A is a unit, then you can of course see that A inverse C minus B, A inverse times C minus B is a solution in R to the equation Ax plus B equal to C. Okay, now keep one thing in mind. It looks like simple algebra. No, you have subtracted B from both sides. That gives you Ax equal to C minus B. Then you have multiplied both sides by the multiplicative inverse of A inverse, which exists because A is a unit. In doing so, however, you have to multiply by A inverse from the left hand side, not from the right hand side. The thing you have to keep in mind is that the ring is not necessarily commutative. It may still be a matrix. I mean, in this ring also you can take in place of A an invertible matrix that will be a unit. So then you can solve the equation, but you have to keep in mind that you multiply by A inverse from the left side, then only A inverse and A will give you the unit element in the ring, and that will give you X actually, so that you can write X equal to this. If you multiply C minus B by A inverse from the right hand side, then that will likely be an error, that will be a mistake. So this is a solution. Now we come to the question of uniqueness in this condition, I mean in this situation. Now suppose x1 and x2 belonging to, we haven't named the ring, no? B, two elements. This is the disadvantage of not naming things. You have to unnecessarily write so many things. Be two elements in the ring that are solutions to Ax plus B equal to C. Then that means what? Ax1 plus B is equal to C, and also Ax2 plus B is equal to C. Hence 0 can be written as C minus C. Now in place of the first C you can write Ax1 plus B, and the second C can be replaced with Ax2 plus B. So you can see that ultimately we end up with A times x1 minus x2. So 0 is equal to A times x1 minus x2. Hence x1 minus x2 can be written as 1 times x1 minus x2, and 1 can be written as A inverse A x1 minus x2, but A times x1 minus x2 is 0, and in a ring when you multiply anything with 0 you get 0. That is x1 is equal to x2. So if A is a unit, not only does the equation have a solution, but it has a unique solution. Okay, and that is not guaranteed if A is not a unit, as we have seen. So in this case, existence of solution and uniqueness both are guaranteed. Although the ring is, it may be any ring, and in fact it may be a non-commutative ring. So here this set of exercises ends. In the next ring video from Gallian, we will see the further things, what comes after this. And tomorrow we have our real analysis, where we are going to address that L sigma problem. Okay, we will we will complete the things about sequences tomorrow. So that's just it for tonight in this video. Signing off from a mathematical room. This is me, Lucifer. Have a nice night.